Is your data. When you're not really asking for output, you're just saying I need to make some changes to my data. Goes before the proc sort.
Thus far, you've taken the first steps in a larger picture of statistical inquiry. You've identified a data set and then used exploratory data analysis to organize and summarize the raw data in a meaningful and informative way. The tools of exploratory data analysis, including examination of frequency distributions, graphical representations of your variables of interest, and calculations of center and spread, help us to discover important features and patterns in the data, and any striking deviations from those patterns.
This all falls under the rubric of descriptive statistics. Put simply, descriptive statistics aims to quantitatively describe or summarize a sample of data.
Now you will be introduced to inferential statistics, which is our ultimate goal.
Inferential statistics allow us to directly test our hypothesis by evaluating, based on a sample, our research question, with the goal of generalizing the results to the larger population from which the sample was drawn. Hypothesis testing is one of the most important inferential tools in the application of statistics to real-life problems. It's used when we need to make decisions concerning populations on the basis of only a sample.
Inferential statistics allow us to directly test our hypotheses by evaluating our research question based on a sample with the goal of generalizing the results to the larger population from which the sample was drawn. Statistical hypothesis testing is defined as assessing evidence provided by the data in favor of or against each hypothesis about the population.
In order to really understand how inference works, though, we first need to talk about probability, because it's the underlying foundation of all statistical methods.
Here's the basic idea. As you know, statistics uses a sample to learn about the larger population from which the sample has been drawn. Ideally, the sample should be random so that it might better represent the entire population. It's very important to acknowledge, though, that this does not mean all random samples are ideal. Random samples are still random, and therefore no random sample will be exactly the same as any other.
One random sample may be a fairly accurate representation of the larger population, while another random sample might not be accurate, purely due to chance. Unfortunately, when looking at a particular random sample, which is what happens in statistics, we will never know how much that particular random sample differs from the population. This uncertainty is where probability comes into the picture. We use probability to quantify how much we expect random samples to vary. This gives us a way to draw conclusions about the population in the face of the uncertainty that is generated by the use of a random sample.
As an example, let's suppose we're interested in estimating the percentage of U.S. adults who favor the death penalty. In order to do this, we choose a random sample of 1,200 U.S. adults and ask their opinion either in favor of or against the death penalty.
An eye for an eye makes the whole world blind. Well, I just don't think violence doesn't beget violence.
Why don't you have them put to death in the way they murdered the person?
Mom.
We find that 744 out of the 1,200, or 62%, are in favor. Here's a picture that illustrates what we've done and found in our example. Our goal here is to infer, to derive conclusions about the opinions of the entire population of U.S. adults regarding the death penalty. Based on the opinions of only 1,200 of them, can we absolutely conclude that 62% of the population favors the death penalty? Another random sample could give a very different result, so we're uncertain. Since our sample is random, we know that our uncertainty is due to chance. It's not due to problems of how the sample was collected. Therefore, we can use probability to describe the likelihood that our sample is within a desired level of accuracy. For example, probability can answer the question, how likely is it that our sample estimate is within 3% of the actual percentage of all U.S. adults who are in favor of the death penalty? The answer to this question, which we find using probability, is obviously going to have an important impact on the confidence we can attach to the inference step. In particular, If we find it quite unlikely that the sample percentage will be very different from the population percentage, then we have good confidence that we can draw conclusions about the population based on the sample. So let's define probability a bit more carefully. The gambling industry makes enormous amounts of money from probability. The casinos know all about probability, while the customers, the gamblers, are trusting blind luck.
You've got the edge, but you've got less of an edge if I've got a good memory and I know some rules of probability.
Absolutely.
Okay.
Absolutely.
Okay. So let's try one or two ideas about probability. If you cut the cards, what are the chances that it's going to be red?
50-50.
Okay, so it's 26 out of 52,
Right.
50-50.
And it was.
All right, it was that time. What are the chances of cutting a spade? Now we got 13 out of 52, 1 in 4 chance.
Correct.
So the odds were always against me.
Right.
So what are the chances of you cutting a king when you've got the whole pack to cut from? 4 of them are kings,
Correct.
52 cards, 1 in 13 chance, yeah? So the odds were never high. How about this one? What are the chances of cutting a king, and then if we do cut a king, we take that out, and now we cut another king? What are the chances of cutting a king each time if after the first time you remove the card?
I haven't a clue. Let's just cut them.
Look at that. Now that's...
Sleight of hand.
It's just the way I do it.
Now let's just try it again, just for
Okay,
close.
close but not there, yeah. What are the chances of cutting a king or a club?
I couldn't figure that out with a calculator.
Now that's quite tricky because we can't just say 4 chances of its being a king, 13 chances of being a club, because actually it might be the king of clubs.
Correct.
Okay, and then one last thing to have a go at. Could we just take the 4 aces out? You've done this before, haven't you?
I have.
I got 4 aces there. Suppose we were interested in getting a particular order. Hearts, clubs, diamonds, spades. What chance have we got that that's the order of those 4? Hearts, clubs, diamonds, spades.
Slim and none.
1 in 4 chance that that's the heart.
Correct.
If it was the heart, there's now a 1 in 3 chance that that's the club. If it was, there's a 1 in 2 chance that that one's a diamond. And if it is, it's a dead certainty that that one's a spade. 4 times a third times a second times a first. 1 in 24 chance.
Probability is defined as the likelihood of something occurring, of an event occurring, the chance of something happening. Probability is a mathematical description of randomness and uncertainty. It's a way to measure or quantify uncertainty. Another way to think about probability is that it's the official name for chance. So what values can the probability of an event take? And what does the value tell us about the likelihood of the event occurring? The probability of an event ranges from 0 to 1. Let's start with those extremes 0 and 1. A probability of 0 means that the event has 0 chance of happening. It will never occur. An event has a probability of 1 if it will occur for certain. In the middle, a probability of 1/2 indicates the event has a 50% chance of happening. In other words, the event is as likely to occur as not to occur. Any probability that is greater than 1/2 indicates that the event is more likely to occur than it is not to occur, and a probability that is below 1/2 indicates that the event is more likely not to occur than it is to occur. Many people prefer to express probability in percentages. Since all probabilities are decimals, each can be changed to an equivalent percentage, so we're actually saying the chance that an event will occur is between 0% and 100%. To better understand the relationship between sample and population, let's consider two simple examples. Here are the distributions of blood types in the U.S. population. You can see the common blood types include type A and type O, with less common blood types, including AB and B. Let's assume now that we take a sample of 500 people in the United States, record their blood type, and display the sample results. If you look carefully, you'll notice that the percentages of each blood type from our sample are slightly different than the percentages of the population. But I'm sure this doesn't surprise you, right? I mean, since we took a sample of just 500 individuals, we can't expect that our sample will behave exactly like the population. But if the sample is random, and this one was, we expect to get results which are not that different from the results of the whole population, and this is what we found. Yet another random sample of 500 individuals reveals results that are slightly different from the population figures and also from what we got in the first sample. This very intuitive idea that sample results change from sample to sample is called sampling variability. Here's another example to help better understand the relationship between sample and population. This example is based on the heights among the U.S. population of all adult males. As you can see, it follows a normal distribution with a mean of 69 inches and a standard deviation of 2.8 inches. Let's say that a sample of 200 males was chosen and their heights were recorded. These are the results of sample 1. The sample mean is 68.7 inches and the sample standard deviation is 2.95 inches. Again, note that the sample results are slightly different from the population results. The histogram we created for the first sample resembles the normal distribution of the population. However, the sample mean and standard deviation is slightly different from the population mean and standard deviation. Let's take another sample of 200 males, displayed here in sample 2. The sample mean is 69.065 inches, and the sample standard deviation is 2.659 inches. This example again demonstrates sampling variability. While the sample results are pretty close to the population results, they're slightly different from the results we found in the first sample. In both of these examples, we have numbers that describe the population and numbers that describe the sample. A parameter is a number that describes the population, and a statistic is a number that's computed from a sample. Parameters are typically unknown because it's impractical or even impossible to know exactly what values a variable takes for every single member of a very large population. Statistics are computed from samples, and each sample of a population is going to have different statistics. The statistics of different samples of a population vary. This is due to sampling variability.
So far, we've been making distributions based on individual variables. Theoretically, we can create distributions for means or proportions taken from multiple random samples drawn from a population. This is the big idea behind inferential statistics.
As an example, suppose we've selected 30 separate random samples rather than only 2, and each of the 30 random samples have 500 individuals drawn from the population of U.S. adults. The first sample has a mean height of 69 inches. We could create a bar graph and plot that mean for our first sample on the graph. If our second sample had a mean height of 68.5 inches, we'd add that to the graph. As we continue to plot the mean height of each random sample, a pattern would begin to emerge. Notice how there are more sample means at 69.25 inches than at any other length. Notice also how, as the length becomes larger or smaller, there are fewer and fewer sample means. This is a characteristic of the sampling distribution, whether we're measuring the mean of a quantitative variable or the proportion of a categorical variable or any other sample statistic. That is, as we draw more and more samples, the distribution of the sample statistics will become more and more normally distributed. This result is known as the central limit theorem, which states that as long as adequately large samples and an adequately large number of samples are drawn from a population, the distribution of the statistics of the samples, whether of mean, proportion, standard deviation, or any other statistic, will be normally distributed. Our projects ultimately rely on only one sample. However, if that sample is representative of the larger population, inferential statistical tests allow us to estimate, with different levels of certainty, parameters for the entire population. This idea is the foundation for each of the inferential tools that you'll be using to answer your research question.
We've discussed probability, the relationship of samples and populations, and the central limit theorem. Now, it's time to begin talking about inferential statistics by describing the steps involved in hypothesis testing. Hypothesis testing is one of the most important inferential tools when it comes to the application of statistics to real-life problems. Hypothesis testing is used when we need to make decisions concerning populations on the basis of only sample information.
A variety of statistical tests are used to help arrive at these decisions. For example, the analysis of variance tests, ANOVA, and the chi-square test of independence, to name a couple. But they all include the same basic steps. Steps involved in hypothesis testing include specifying the null hypothesis, H subscript 0, and the alternate hypothesis, H subscript A, choosing a sample, assessing the evidence, and drawing conclusions. Statistical hypothesis testing is defined as assessing evidence provided by the data in favor of or against each hypothesis about the population. To provide an example of hypothesis testing, we're going to use the NESARC data set, a representative sample of 43,093 adults in the United States, to evaluate whether or not there's an association between a diagnosis of major depression and how much a person smokes. We're going to work through the example using the 4 steps, specifying the null and alternate hypotheses, choosing a sample, assessing the evidence, and drawing conclusions. First, there are 2 opposing hypotheses for this question. The null hypothesis, commonly shown as an H subscript 0, is that there's no difference in smoking quantity between people with and without depression. The alternate hypothesis, shown as H subscript A, or sometimes shown as H subscript 1, is that there is a difference in smoking quantity between people with and without depression. The null hypothesis basically says nothing special is going on between depression and smoking. In other words, that they're unrelated to one another. The alternate hypothesis says that there is a relationship and allows that the difference in smoking in those individuals with and without depression could be positive or negative. That is, individuals with depression may smoke more than individuals without depression, or they may smoke less. After stating the null and alternate hypotheses, we need to choose a sample. We're going to use the NESARC data set, and we're only going to evaluate these hypotheses among individuals who are smokers and who are younger rather than older adults. We subset the NESARC data to individuals that are 1. Current daily smokers, that is, they've smoked every day in the month prior to the survey, and 2. Are age 18 to 25. This sample, N equals 1,320, showed the following. Young adult daily smokers with depression smoked an average of 13.9 cigarettes per day, with a standard deviation of 9.2 cigarettes. Young adult daily smokers without depression smoked an average of 13.2 cigarettes per day, with a standard deviation of 8.5 cigarettes.
While it is true that 13.9 cigarettes per day are more than 13.2 cigarettes per day, it's not at all clear that this is a large enough difference to reject the null hypothesis, or to say that smokers with depression smoke significantly more than smokers without depression.
While it's true that 13.9 cigarettes per day are more than 13.2 cigarettes per day, it's not at all clear that this is a large enough difference to reject the null hypothesis, or to say that smokers with depression smoke significantly more than smokers without depression. So now we need to assess the evidence in order to determine whether the data provides strong enough evidence against the null hypothesis, that is, against the claim that there is no relationship between smoking and depression. We really need to ask ourselves, how surprising or rare is it to get a difference of 0.7 cigarettes smoked per day between our two groups, that is, those with depression and those without, assuming that the null hypothesis is true, that there is no relationship between smoking and depression.
This is a step where we calculate how likely it is to get data like this when the null hypothesis is true. In a sense, this is really the heart of the process, since we draw our conclusions based on the probability estimate. The null hypothesis is generally assumed to be true until evidence indicates otherwise.
The probability that we'll get a difference of this size in the mean number of cigarettes smoked in a random sample of 1,320 participants is roughly 0.17 or 17%. We'll talk about how this gets calculated for the different statistical tests later. The important point at this stage is that it's this kind of evidence that we will be considering every time we decide to accept or reject the null hypothesis. So how exactly do we use this probability to come to a conclusion about the null hypothesis? Remember, if the null hypothesis is true, there is no association. There's a probability of 0.17 or 17% of observing this size of difference between smokers with and without depression. The translation of this 17% probability is that if we took 100 random samples from our population, we would be wrong 17 out of 100 times if we rejected the null hypothesis and said that there was a difference in smoking quantity for smokers with and without depression.
Now we have to decide whether or not this is something that we feel comfortable about. Do we mind making a mistake in saying that there is a difference in smoking quantity 17 out of 100 times? Does this probability of 0.17 make what we're observing rare enough to make us feel confident about rejecting the null hypothesis?
We can all probably agree that a probability of 0.50 would certainly not give us enough confidence to reject the null hypothesis, because 0.50 or 50% means that we would be right 50 out of 100 times and wrong 50 out of 100 times, no better than making decisions based on the flip of a coin.
Being wrong 17 out of 100 times would make us far less likely to be wrong in rejecting the null hypothesis. But we would still be less certain than if the probability were even smaller, say 10 or even 5%. Basically, this is our decision when testing hypotheses. In order to make this decision, it would be nice to have some kind of guideline or standard. What probability would give us confidence in rejecting a null hypothesis?
The reason for using an inferential test is to get a probability value, commonly called p-value. The p-value provides an estimate of how often we would get the obtained result by chance if, in fact, the null hypothesis is true. In statistics, a result is called statistically significant if it's unlikely to have occurred by chance alone. The most commonly used standard or cutoff is 0.05 or 5%. Because this standard or cutoff is so important, it has a special name. It's called the significance level of a test and is usually denoted by the Greek letter alpha. So alpha equals 0.05. If the p-value is small, less than 0.05, this suggests that it is more than 95% likely that the association of interest would be present following repeated samples drawn from the population, aka a sampling distribution. If the p-value is less than alpha, which is usually 0.05, then the data we got is considered to be rare or surprising enough when the null hypothesis, H subscript 0, is true. And we say that the data provides significant evidence against the null hypothesis. So we reject the null hypothesis and accept the alternate hypothesis, H subscript A. If the p-value is greater than alpha, then the data is not considered to be surprising enough when the null hypothesis is true, and we say that our data do not provide enough evidence to reject the null hypothesis, or equivalently, that the data do not provide enough evidence to accept the alternate hypothesis.
So finding a p-value less than or equal to 0.05 means that the finding is statistically significant, and we can reject the null hypothesis and accept the alternate hypothesis.
This p-value is also known as the type 1 error rate, since it denotes the number of times we would be wrong to reject the null hypothesis when it was true. Rejecting the null hypothesis when it's true is also called a type 1 error. Looking at the p-value in our example, we see that there is not adequate evidence to reject the null hypothesis because the p-value was 0.17, which is definitely greater than 0.05. In other words, we do not reject the null hypothesis that there is no association between depression and number of cigarettes smoked among daily young adult smokers. We accept the null hypothesis. There is no association between smoking and depression because the data does not provide enough evidence to accept the alternate hypothesis that there is an association between smoking and depression. Let's change the research question slightly to demonstrate that the decisions you make about your sample and your variables can impact your findings and the conclusions that you draw. Using our example, we're still interested in the association between depression and smoking. However, we decide to not limit ourselves in considering only individuals who smoke daily. Let's look at a broader population of young adults and consider those that have smoked at all in the past year, whether daily or more irregularly. The size of this sample in the NESARC dataset is 1,706. With this sample, we find that young adults with depression smoked an average of 351.7 cigarettes per month, with a standard deviation of 300 cigarettes. Young adults without depression smoked an average of 313.5 cigarettes per month, with a standard deviation of 268.2 cigarettes. So the difference between quantity of cigarettes smoked among young adults who smoked in the past year, with and without depression, is 38.2 cigarettes per month, almost 2 packs. The p-value of this revised scenario is 0.0285, obviously less than 0.05. This means that the probability that we would get a difference of this size in the mean number of cigarettes smoked in a random sample of 1,706 participants is less than 3%, which is a p-value of less than 0.05. So in this case, we can reject the null hypothesis and say that young adult smokers with depression smoke significantly more cigarettes per month than young adult smokers without depression. If we look again at the number line of probabilities, we can translate this finding in the following way. If we reject the null hypothesis and say that there is a difference between the average number of cigarettes smoked per month among young adults with and without depression, we would be wrong fewer than 3 out of 100 times. We'd be correct more than 97% of the time. Based on the standards of science, this is a level of certainty that gives us confidence in saying that there is a significant association between smoking and depression among current young adult smokers.
You've been introduced to the general process of hypothesis testing. It's time to learn how to test your own hypothesis. You will always be interpreting p-values, regardless of the inferential test that you use. The specific statistical test that you use to evaluate your hypotheses will depend on the type of explanatory and response variables that you have chosen.
These are some bivariate statistical tools and the situations in which you use them. The term bivariate here refers to 2 variables, explanatory and response. If you have a categorical explanatory variable and a quantitative response variable, you would use an analysis of variance, ANOVA, as your inferential test. If you have a categorical explanatory variable and your response variable is also categorical, you would use the chi-square test of independence as your inferential test. If both your explanatory and response variables are quantitative, you would use a correlation coefficient as your inferential test. If your explanatory variable is quantitative and your response variable is categorical, you would categorize your explanatory variable with only 2 levels and then use the chi-square test of independence as your inferential test.